point here and then join them together, right? Are you saying this is a ball?
Yeah, so that's the ellipse symbol.
But you said this is a ball? Is the same as this ball?
Yeah, is that true? That's C X. Yeah, so C is the curve from A to B.
C
It gives the
yeah.
path from A to B.
Uh-huh.
And you look at all the points. All the points to the. Yeah, I think that's true.
But why is this a ball?
It's a cone over sphere.
Cone over a sphere.
Like it's just like a.
Oh,
sphere getting smaller, and then.
Oh, you mean ball is a ball in a lower dimension?
No, I mean the n+1. If you're starting with a sphere, and then the radius getting smaller and smaller. And then it's become like if you think a cone over a circle, that's a disk.
It's a disk, yeah, right.
So the ball, I mean, if the sphere is shrink the radius to 0, that is ball.
So that means this VC is taking the radius, the boundary of this ball.
Yes.
So that means.
Yes, that is BC. Okay, so this.
So that means so that means this Lagrangian this Dehn twist is actually doing Dehn twist on the boundary of the Lagrangian sphere you form.
Yeah, I think so. I think that is.
But can you picture that thing or not? Like, let's say I got this sphere here, then I take the boundary, this the whole because this is like R3.
If the green thing you draw in the picture is the ball, then where is X naught?
Where is S naught? Where is S naught? This one S naught.
Oh no, I mean the big picture there.
The big picture. Oh, S naught is on the fiber on top of this. S naught.
Okay, so then X naught is the.
I think S naught is the point that map to CB.
Yeah.
Yeah.
Then the boundary of this ball contains X naught.
Contain S naught.
X naught is the.
No. The country. No. Like for example, for this case, S1, right? I think I get what you mean. No. Because because for example, if it is X1 and then you keep going out, you become this. So S0 is here, boundary is outside, right?
Yeah, so the VC is in the fiber over CA.
VC is in the fiber over CA.
Yeah, so this VC, yeah, I think that is it is. You have this fiber which is ECA. ECA is the fiber over CA.
Oh yeah, because in this case we also take the most outside the one coming from CA, right? Yeah, because the lowest layer is CA.
So this is if we on the homology class, this will be the Picard-Lipschitz formula. Here is on actual actual sphere. The Y is the Dehn twister. Monodromy means the Dehn twister.
Yeah, the proof is like, if Brian, you have time, maybe you can look at the proof, because I don't understand the proof.
Which the same calculate by this.
A long exact sequence.
A long exact sequence.
I don't understand. Like, I don't see why it proved that it is a model Dehn twist, but I don't see why. And then he talked a lot about the cutoff function thing.
Maybe I have a look at. So
yeah, I already write down the reference. This is the proposition 1.1.
Okay. We'll put the file in the Dropbox. Maybe I'll have a look at.
I'll put the file. Okay. And then Oh, okay. Anything want to talk about this, or I say one last thing about the?
But that's all today. You may want, maybe you can continue next time.
Yeah. I just want to say like this these Dehn twists here give break relation. So they break. And how they show they break is like using the Lagrangian surgery. Is like what you said, the connecting sum.
Okay.
Yeah.
So maybe we'll leave that till next time. And next
But
time maybe I will explain monodomy around L is as topic to the. I will explain this proposition.
And those these kind of proposition, right? Like very analysis and very use a lot of look at a lot of like weird function, and then I don't know. Some part I don't understand. They have to put it back to Cn, and then sometimes they can do it there, and then they restrict back and then get back leaf shape vibration, and then they say the argument will follow, and then like.
So have you put in that in Dropbox? Maybe can you maybe share the file?
Yeah.
Maybe share the file. Can maybe just for a few minutes we
share now. Okay.
Yeah, you can share the file
Okay,
on your computer.
Okay, I try. Let me see.
There's a share. I think there is a share. If you're on a computer, you can share and click share. Then there's options: share desktop, and share even file. If the file is open in the computer, you can share the file.
Okay, let me find. Maybe I search it faster.
Do I have another?
Long. Wait, let me see.
Maybe I can search from the computer and then share my screen.
A lot of privacy setting.
Okay, I will share mine. I can.
Okay.
Just, you see my screen?
Yeah.
Okay. So you see my please web browser is
Not yet. Page 19.
would like to see the paper, not the provider.
Yep.
No.
Page 19. Yeah, this one. Yeah, this one.
Then the monodromy I want L is connecting twist. The proof actually a few pages, quite long. Right? Feel like
Yeah.
Two pages, provable 2 pages.
I think one lemma is quite important, which I can't see how to show the monodromy is the Dehn twist. There's a one lemma 1.10. I think that one is quite important, but I can't see.
1.10.
10.
This one?
Lemma 1.10. Which one?
So
This one. Yeah, this one.
Maybe the close disk radius. That is on the base. Then there is reductor operation over. So that's a small disk together with isomorphism ER to T lambda.
I think this proof tell you how to see the monodromy as a Dehn twist, but I can't understand.
Actually, that follow how denote U is in fact monodromy in positive sense. And then with the model. Okay, so here is the proof. Okay, 3 or 4 pages now. Okay, so this I can't just like look at it. This is what is diffeomorphism. So that is. So this is power transport along the along the boundary.
Because you can pick the boundary. ER is the Mueller fiber, and then T lambda R is some.
What T lambda? T lambda
L is T lambda is ER and T lambda R is like you see the Mueller fiber as a cotangent on the. Lambda is the length of the cotangent vector.
So, incidentally, this is related. This is the symplectic Picard-Lefschetz theorem, is it? Related
Right.
So in the notes that Brian told us about this course by Seidel, right? For Kaya categories and Picard-Lefschetz theory.
Yep.
On page 224.
224.
At the bottom, he states it and then he says, we will not give the proof here, but it's maybe worthwhile summarizing the basic strategy. And there's the 10 lines of summary of basic strategy, which may help you understand the proof, perhaps.
Which page? Page 2.
224, bottom of 224, top 224. Of 225. I haven't read it, I haven't understood it, but I see that there's 10 lines of summarizing the basic strategy.
Yeah, I see that.
Okay, so that we say that there is a vector fields, which is yeah, maybe I will look at explain this. These things are important. Okay. Yeah, both this lemma is non-commutable. Oh, look at this. So maybe there's a vector field on the Lipschitz vibration, and then integral on the curve. This is very explicit.
Very explicit.
Lemma. I try to figure out a better way to prove this. And we have the sphere. It's different symplectmorphism. Yeah, maybe this symplectmorphism, the power transport is defined by the vector field. The power transport, that is horizontal vector field. So maybe there is a way locally. So this is near the vanishing cycle. If we have look at examples. Like examples, maybe the in two-dimensional examples, like just n is 1. Maybe you can think that as you have vanishing cycle. And this have to be in a local model. Try to see them.
Actually, I found a paper drawing the small example, but I don't see how, like, why can they draw like that? If you want, I can send you the paper.
Okay. And do you share screen from the demo? We don't have.
Yeah, sure. I need to find the name first. Okay, sure. I find the name. I forget which paper. Let me find the name.
Yeah, this theorem by Seidel is this the fourth theorem in the introduction is important in the Sky category. Essentially,
Triangulated, is it?
Derived in the case derived triangulated. So you have the exact sequence triangulation. So if you look at the category point of view, with Lagrangian flow theory is a morphism between two Lagrangian.
Whereabouts is this paper? It's in the Dropbox on gauge
Maybe
theory.
the Kinting will put this paper in the Dropbox.
Okay, I can put them on.
Oh, we don't have
I
it
know
at the
the paper,
moment.
but I never read it because
Find the example.
Do we have the paper at the moment?
I think Kinting will put it. Maybe I can put it. I can save it to the.
Okay, so it's not in the Dropbox at the moment.
Not in box moment. Okay, maybe I do it now.
Yeah, wait.
Okay. Then I'll put in the Sakai category. Okay, so now this is Sidle, the non-exact triangular, the sequence, maybe. Okay, so now it's in the Dropbox. And yeah, actually, this if you look at the Sidle's theorem, say the original inspiration for this comes from that sequence in Donaldson flow theory, which can be translated into simplex geometry using various versions of TF-Lowry conjecture. These line of thought should have a subwritten siblings. Yeah, okay. And
to calculate the Picard-Lipschitz formula, you need a intersection form.
yes.
But that one is depend on your manifold, is it?
Yeah, that's general theorem. That is for yeah, maybe we will some noise here. Okay, so maybe next time we will look at yeah, maybe next time I will give some talk on this paper, some of this before looking at the bread relation, because they then twist. This theorem is very important for the yeah. Oh. You can think something which is here. Right. I couldn't write on this.
Brian, if you want to draw on it, you can just open it up on your laptop rather than through Chrome, and then you can go into the options and draw it.
Oh, I see. Okay. Maybe can still see my desktop.
Yep.
Here you can mean essentially this sequence this is sequence on the morphism. So you can
Are you trying to draw, Brian?
yeah.
So click, I think, markup on the bar over there next to rotate and highlight. So move your mouse to the right, up, 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 up a little bit, right there. Yeah, click that down there. There should be markup. You should better press that.
Okay.
Next to the search thing on the left-hand side of the search. Can you press that? No, to the right, up, right.
Left.
Oh, is it
Left
right?
text
No,
draw. Or maybe it's color. Okay, I think it's at the moment the color is white, right? So maybe okay, because I couldn't see it. That's it's drawing white on the. If I'm thinking, if you look at this, if you're starting Lagrangian, so you're starting with Lagrangian sphere, which is L, and then you have LA2 Lagrangians. So you apply the don't twist to one of them, and is L. I think it's L1. What I'm saying that with L1, you can think this L1 is variables. So in some way, we can talk in the Fukaya category by look at the triangular in the object. So we have tau L applied to L0. Or maybe it's like L1, L0. I think it's tau 0, and then this will be L0, and then L0 to L0, 1. And so this will be vector space. L0, L, and then I think it is tensor with F, with F, yes. I think it has some sequence like this on the object level. Then you apply, so this like these are 3 objects in Fukaya category. Of course, this is in terms of vector space. So this is, and then this sequence essentially like the morphism of applied to the whole thing to L1. Right, so that is so these triangulars. So these triangulars. So that you make the Fukaya category. So derived Fukaya category of triangulate Fukaya category. And this make triangulated Fukaya category. Okay, so maybe next time I will try to cover some of the results here in this paper. So before we look at the bread relation, so essentially in some way in that example, so we have this Lipschitz vibration. Okay, so if we go back and we look at we have a Lipschitz vibration. And then Lipschitz vibration. Then we want to find the Fukaya category of this. And also Fukaya category of the fiber. A fiber of some fiber of this some points C, regular valued. And then if we take Lagrangian spheres, so for example, these are vanishing cycles. Then we can have this Dehn twist term. And this Dehn twist term is a symplectomorphism of the fiber, say EC. And then we have this relation. Essentially, we have say pi grade relation, pi 1. So from say C, D remove the say A1, AR, and to the pi 0 of symplectomorphism of EC. Okay, so this is the representation, right? That's contained. So this is what you want to prove. So you want to have prove a bread relation on this level. Right?
It's faithful, yeah.
Faithful, okay. So before that, we need to understand this Dehn twist. That's before we look at the bread relation, we understand more about the Dehn twist. So actually, I never read this paper before. Maybe I will have a look. Try to make sense and try to give. Okay.
I can't find the paper now, but later after I found, I send you like there's a small example of Dehn twist on symplectic topology.
Okay, okay. But I mean, probably we can stop today, and then next week we try to understand some of these key proposition or some from this paper.
Mm-hmm.
Okay, so at least this theorem is important for the Fukaya category, but we need to understand this.
Okay.
Okay. So maybe we just we stop the meeting today already. Moment after 12 o'clock. Maybe any question? If not, we meet next time.
Okay.
Yeah, so it's better we go through the details and then just assume that. Yeah, so next time we'll look at more of this. I will check if I can understand some of this and give a talk.
Okay.
So at some stage, maybe everybody should volunteer to read something and present. So maybe all right. So then let's stop the meeting now.
Okay. I'll put reference there on later.
Yes.
Thanks, everybody.
Okay. Bye.
Bye.
Bye.